Okay, here is a AP2 question that appeared a couple of years back from an AP exam. It was a challenging problem for an AP2 exam. It takes a while. Here we go. We're going to start off by using the continuity equation and then going to Bernoulli's equation and then projectile motion stuff, kinematics and projectile motion. So everything all here. But here's what we got. We got a pipe underground. The pipe underground has a radius of 1/10 of a meter. And the pipe makes this turn. The pipe reaches the surface of the ground. And here at the surface of the ground, now the radius is 0.05 meters. So it's been cut in half. The radius of the pipe is half at the surface what it is underground. First question is, what's the speed at point A, the V over here? The problem tells you over here the speed is, this is radius, and they tell you the speed over here is 8.2 meters per second. So you could figure out, you right away to your continuity equation, area 1, velocity 1 equals area 2, velocity 2. Area, you should recall, is pi r squared. So you could plug this into here. You got pi r1 squared times volume, speed 1 equals pi r2 squared volume 2. Sorry, I want to say volume, speed 2. Pi's cancel out. So basically the radius squared in one spot times its speed equals the radius squared times its speed in the second spot. It's connected to the square. If you double the radius, which is what's happening when you go from B to A, you double the radius, and it's radius squared. If you double the radius, the speed is going to go down by a factor of 4. I know right away the answer is going to be 8.2 divided by 4. It's going to be 1/4, right? But let's do the math anyway. Here we go. Radius 1, 0.1 meters squared times speed 1, which is what we want to know. The radius 2, 0.05 meters squared times 8.2 meters per second. Grab our calculator. Let's do the arithmetic. 0.01 squared. No, sorry. 0.1 squared is 0.01. You know that. Goodness. Make sure your calculator's into the right modes. So 0.01 meters squared times speed 1 equals 0.05 squared. Times 8.2. Divide both sides by our 0.01. I'm running at V1 equaling 2.05 meters per second. Now, again, if you go through just relationships, if you double the radius and it's connected to radius squared, you're going to do 1/4 the speed up top. So 8.2 divided by 4 gives you, guess what that gives you? 2.05 meters per second. If you recognize relationships, it saves you a little time. All right, so that's the first part of the problem. 2.05 meters per second. Calculate the absolute water pressure at the pipe at point A down here. Oh, goodness. This is a challenge. This is a challenge. Here we have to use Bernoulli's equation. Anytime you have Bernoulli's equation, write out the whole equation. P1 plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. Couple of things. Set the lowest point at your 0. There's your 0. So we'll call A 1, the ground here 2. If this is 0, that's going to go away to 0. We want to know the pressure here, the absolute pressure here. We know its speed. We just figured out the speed. So we can figure out its kinetic energy. So we're going to get P1 plus 1/2 density of water is 1,000 kilograms per cubic meter times its speed, 2.05 meters per second squared, equals. We can even do that side of the equation now if we wanted to. 0.5 times 1,000 times 0.025 squared, 2,101. So the left-hand side of our equation is going to look like this. 2,101.25 pascals equals. All right, P2. What's the pressure going to be here? The absolute pressure here is going to be atmospheric pressure, right? That's 100,000 pascals. It's standardized. Plus, now this is at a height of 1/2 meter. So we're going to go rho, 1,000 kilograms per cubic meter times 9.81 meters per second squared times the height, 0.5 meters, plus 1/2 rho, 1,000 kilograms per cubic meter times the speed. The speed over there, if we recall, was 8.2 meters per second. 8.2 meters per second squared. All right, let's do our arithmetic. 100,000 pascals plus, let's add this up, 1,000 times 9.81 times 0.5, 4,905. 4,905 pascals plus 0.5 times 1,000 times 8.2 squared, 33,620 pascals. We're going to find for P1. So add all these up. P1 plus 2,101.25 pascals equals 100,000 plus 4,905 plus 33,620 gives us 138,525 pascals. So P1 is equal to 136,423.75 pascals. Now that's maybe a little too many significant digits. What do we have here? We had 2 digits here. Looks like everything's going to the hundredths or so. So basically we've got, even if we were to say the absolute pressure was a 1.364 times 10 to the 5th pascals. Pressure at A, the absolute pressure at A. Something like that. Okay. let's change the less a bit. So absolute pressure at A, 1.364 times 10 to the 5th pascals. Now the next two problems, they're not with really fluids. They're reviews of kinematics and projectile motion. But we'll go through them anyway. We'll go through real fast. Number 3, calculate the maximum height at which the water reaches the ground, shooting up at. So give yourself some space here. Come back here. The water comes out of the pipe. It's flying up at 8.2 meters per second. It's going to reach the peak. The speed at the peak will be 0. The question is, what height does it get to? Right, we know the final speed. We know the initial speed. We also know the whole time it's on planet Earth, so its acceleration. Vf squared equals Vi squared plus 2AD. The Vf is going to be 0. The initial speed, 8.2 meters per second, plus 2 times 9.81 meters per second squared, delta D. All right, so kinematics equations, pretty simple. Rearranging things. Negative, bringing this over there, negative, that's also negative, negative 67.24 meters squared per second squared equals 19.62 meters per second squared times the change in height divided by 19.62. Delta D equals 3.43 meters. All right. And now problem 4. How far from the ground will water reach if it goes at an angle of 60 degrees? All right, well, some of the water's coming straight up, but as from that pipe from underneath the ground, some of it's going straight up, but some of it might be shooting this way, some of it might be shooting that way, right? So this is ground level, and that's 60 degrees, and this is still 8.2 meters per second. We want to know the range. How far does it go? Well, here you got to go back to projectile motion. You got to figure out, you got the sideways speed is 8.2 meters per second times the cosine of 60 degrees. The vertical speed is going to be 8.2 meters per second times the sine of 60 degrees. We got to figure out how long it's going to be in the air, the whole thing there. So let's go from that. Vf equals, got to figure out the time, right? How long is it going to take to get to the peak? So at the peak, the speed is 0. The initial speed in the y direction is 8.2 times the sine of 60 degrees plus negative 9.1 meters per second times time. So 8.2 times the sine of 60, so halves, all right, 7.1. Divide that by 9.81. So time to the peak is 0.7238 seconds. Multiply that by 2 for up and down. Time of flight is that times 2, or basically 1.45 seconds. 4.4778.9, whatever, something like that, around to the hundredths of a second. So the total time of flight is going to be that. Now the range distance equals VIT plus 1/2 AT squared, all in the x direction. Right, there is no acceleration in the x direction, so that goes to 0. So the range is equal to the initial velocity in x times the time of flight. The range is equal to 8.2 meters per second times the cosine of 60 degrees times 1.45 seconds. The range would be 8.2 times the cosine of 60, which is half. So 4.1 times 1.45 seconds. 5.95 meters. Done.